Hello students. Today we are going to learn about phase equilibrium. Now, to understand phase equilibrium, we need to understand three different terms, which are the major terms involved in phase equilibrium. That is phase, components, and degree of freedom. Now, phase equilibria is basically an application of chemical thermodynamics. So over here, you can see a cat observing this jar. So here you can say that this jar is acting as a system. Now in this system, you can see blue colored balls and red colored balls are being layered. Now, if I'm asking how many phases are there in the system, how many components are there in the system, how will you calculate the degree of freedom for the system? All these question marks would be resolved by the end of this video. Okay. Now, before jumping into different examples, we will be looking into the definitions first. So, first we will see what is a phase. So over here, you can note down the definition. Now in this definition, the important part is homogeneous, physically distinct, and mechanically separable part. Okay, so in this system, you have to observe what are the homogeneous, physically distinct part, and it should be mechanically separable. In simple language, you can say that you have to detect how many solids, liquids, and gases are present. Okay, this will be clear with when we will see different examples. Okay, now let us see components. Okay, one more thing you have to observe that phases are denoted by capital P. Okay, now looking into the components, you can note down the definition. Component is denoted by capital C. Now in components, you will check the independent variable constituents by means of which the composition of each phase can be expressed directly. Simply, if I'm taking an example, argon gas. Okay, this argon gas is in equilibrium with water. So, how many constituents you can see? You can see one argon gas and you can see water, right? Other than that, nothing. So, number of components would be two. Okay, if I'm considering only water, then in this case, number of components would be 1. We will be looking a lot of examples with which your concepts would be clear. Now, degree of freedom, which we have to calculate. And this degree of freedom you can calculate by this formula F is equal to C minus P plus 2. Now over here, you can understand that F is degree of freedom, C is number of components, and P is number of phases. Remember that degree of freedom is also known as variance. Now, by calculating degree of freedom, what we are going to understand, we will understand how many variables are required to define a particular system. Whether temperature would be sufficient, or we need temperature as well as pressure, or we need all the three temperature, pressure, as well as concentration. Okay, for example, if I am getting the value of F as 1, this indicates that the system will require either temperature or pressure or concentration. Any one of the independent variable would be required. If it is coming out to be 2, this indicates that it will require temperature and pressure or temperature and composition. Means two independent variables would be required to define that system. Okay. Now let us understand all these terms with the help of some examples. Okay. So first of all, let us consider this example. A simple glass of water is kept on the table. So here you can see that our system is a glass of water, right? Now in this system, what you can observe, you can see the water which is in liquid state. Other than water, nothing is available over here, right? So if I have to write this, we can say that water in liquid state, this is our system. So if I have to calculate the degree of freedom, first step is you will calculate how many phases are there here. So over here, you can see liquid water. You cannot see other states, right? So number of phases would be one. Only liquid water is present. How many components can you see other than water? Anything else is present over here? No, right? So only water is present, only component present over here is water, which is defining this space completely. So the number of component is 1. And over here, you can calculate the degree of freedom by the formula F is equal to C minus P plus 2. Number of components, we have identified it as 1, phases 1 plus 2, which is a constant. So 1 minus 1 plus 2, it is coming out to be 2. Hence, we can conclude that a glass of water kept on this table is a monovariant system. Now, monovariant system, sorry, not monovariant, it is bivariant. Okay, because degree of freedom is 2. So it is a bivariant system. Bivariant indicates that you will require temperature and pressure, or temperature and composition. Or you can say you will require pressure and composition. Means any two of the independent variables would be required to define this system. Okay, now let us move on to the next example. Now, as you can see that summers are approaching and we all like cold water, right? So here, if I'm observing this system, now you can see a glass of water with some ice cubes over here. So you can say that here you can observe water in liquid state and water in solid state. These are the two different states, two different phases you can observe. So chemically, if I have to write this system, I can say that water, which is in solid state, it is in equilibrium with water in liquid state. Okay. So here, if I have to calculate the number of phases, how many phases are there? You can see a solid ice, solid water, and liquid water. Two phases. And you know that phase is physically distinct, mechanically separable part of the system. Physically, I can see ice and water and I can mechanically separate it, right? Simply by putting a spoon, I can separate this ice. Okay, so number of phases would be 2. Number of components. How many constituents are present over here? Other than water, you cannot observe anything else, right? So the number of components over here is 1. Only water is present. Other than that, nothing else is present. Okay, so degree of freedom F is equal to C minus P plus 2. C value it is 1, phase is 2. So 1 minus 2 plus 2, it is coming out to be 1. So F is equal to 1 indicates that our system is monovariant. Now, if the system is monovariant, it indicates that either temperature or pressure or composition would be required to define this system. Okay, now let us move on to the next example. Now, what is happening over here? You can see the glass of water is kept on a gas burner. Now the water is being heated. Now guess the number of phases over here. Yes, you can see water in liquid state, which is kept inside the glass, which is being heated, because of which you can see the water vapors over here. So water vapors, I can represent it as water in gaseous state. Right. So if I have to write this system chemically, I can write it as water in liquid state. It is in equilibrium with water in gaseous state. Okay. So this is our system here. Now the number of phases over here. How many phases can you see? You can see a liquid water and the gaseous water. This is our system. And in the system, you can see two different phases, physically distinct, mechanically separable part. You can see number of phases, 2. Number of components other than water, nothing else is visible over here. So in the system, only water is present. So number of components, 1. Now to calculate the degree of freedom, we know the formula F is equal to C minus P plus 2. 1 minus 2 plus 2. Again, I am going to get degree of freedom as 1, which indicates this is also a monovariant system where a temperature or pressure or composition would be required to define this system. Now, I've kept an ice cube over here and the temperature is very high. So in this case, you can see water in liquid state. Okay, water in liquid state is present over here. Other than that, ice cubes are also present. So water in solid state is also present. And you can see water in gaseous state. The solid ice is getting converted into gas as well. So over here, if I have to represent this system, I can say that solid water is in equilibrium with liquid water and it is in equilibrium with gaseous water. Okay, so over here, we can say that the number of phases would be three because you can see a solid state, liquid state, and gaseous state. All the three states are visible, all the three phases are visible, which is physically distinct and mechanically separable components. Now, if I'm talking about the component, only water is present, so the number of components would be one. So, in the similar fashion, you can calculate the degree of freedom C minus P plus 2. So 1 minus 3 plus 2, which will come out to be minus 2 plus 2. Hence, the degree of system over here is 0. So in this case, the system is non-variant, which indicates none of the variables are required to define the system, neither temperature, nor pressure, nor composition. Okay, now let us see a different example. Now these are brass tubes. Okay, so brass is an alloy, right? So if I am talking about the number of phases, how many phases are present over here? So what would be your guess? Here, brass. If I'm talking about the alloy, you can say that brass is an alloy of zinc and copper. So here you can see zinc as well as copper. But if I'm asking how many phases are there, so you would be saying that two, right? But it is not two. Brass is visible. But can you identify zinc and copper? What is the definition of phase? Physically distinct and mechanically separable. Is zinc and copper physically distinct that both elements are different? Can you distinguish it? No, right? So the number of phases in case of alloy would be 1. Okay, alloys number of phases would be 1. If I'm talking about the number of components, then how many components are there over here? You can see zinc and copper, right? I have specified it as zinc and copper. So in this case, you can mention the number of components as 2. So if I have to uh, calculate the degree of freedom in this case, so F is equal to C minus P plus 2. So number of components, 2. Number of phases, 1. So 2 minus 1 plus 2. That is coming out to be 3. Okay. Now over here. Now here you can see I have drawn allotropes of carbon. So in case of allotropes, you know that carbon has three allotropes, right? That is graphite, diamond, and C60 fullerene bond. So I have mentioned all the three over here. Now, if I'm keeping a pencil and diamond, you can physically identify it. It is physically distinct and mechanically separable. So in case of allotropes, number of allotropes would be equivalent to number of phases. So in case of carbon, we can say that the number of phases would be 3. Okay. And the number of components definitely 3. You can see 3 different elements over here. So sorry, the number of components would be 1 because all the 3 elements are made up of carbon. So the number of components over here would be 1. Okay. So basically, we have to identify the number of phases. Now let us look on to this system. Now, what is happening over here? I have added some table salt, NaCl salt. So this is your NaCl salt, which is being dissolved in water. Okay, now there are two cases. If I am adding 1 tablespoon of NaCl or 2 tablespoon of NaCl, it would be completely dissolved, right? And we will get a clear solution over here. So in this case, if I am asking how many phases are there, you can say mechanically separable or physically distinct, you can see only a liquid phase over here. So the number of phases would be 1. But what if I am continuously adding the salt? I am adding 20 tablespoons of salt in a glass of water. It won't be dissolved, right? You can see solid particles as well as liquid particles over here. So in this case, the number of phases would be 2. Okay. And in this way, you can calculate the components and degree of freedom as well. If I'm asking about the components. So over here, you can see two different components, NaCl and the other component is water. So number of components would be 2. And in this case, number of components again, NaCl and water. So the number of components 2. Okay, degree of freedom, it is very easy now. You can easily calculate with the formula F is equal to C minus P plus 2. Now the example, the system which we have started. Okay, the very first image which we have seen. The cat is observing this jar. Now you can see two different colored beads. One is blue colored bead and the red colored bead. Both are in solid state, right? So if I am asking how many phases are there, so what would be your answer? Just imagine you are having a jar filled with dairy milk and Kit Kat chocolates. So you can physically see that Kit Kat is different and dairy milk is different, right? So it is physically distinct and mechanically separable. You can easily separate out Kit Kat and dairy milk, right? Similarly, over here you can see blue colored ball and red colored ball. Both are different solids, right? So the number of phases would be 2. So what we can conclude over here, the number of solids, it would be equivalent to number of phases. Okay, if I am having NaCl in solid state and if I am having copper sulfate in solid state. Okay, so these are the two different solids, right? Two different solids, so number of phases would be 2. If I am adding one more solid, number of phases would be 3. So the number of solids would be equivalent to number of phases. Okay, again components. What would be the components? NaCl and copper sulfate. So number of components 2. Degree of freedom you can easily calculate. Now imagine you are holding balloons. Okay, I have given you a yellow colored balloon. Now if I am asking, in this balloon, how many phases are there? So what would be your answer? How many phases would be there in this? Here, if I am specifying, I have filled this with oxygen gas. What would be your answer? The number of phases would be 1. Only gaseous state, right? Only gaseous oxygen. Now imagine I have given you this violet colored balloon. And this balloon is filled with helium gas and oxygen gas. Now, in this case, what would be your answer? How many phases are there? Again, your answer should be 1. So, what we can conclude over here, number of gases. Okay, if you are an n number of gases, the number of phases would be always 1. What is the reason? Because if two gases are mixed with each other, we cannot physically identify how many gases are there, right? How many components are there? We can tell if it is specified how many gases we have filled. Until and unless if I have mentioned helium gas and oxygen gas is present in this purple bulb, you wouldn't have answered that the number of phases or you wouldn't have understood how many gases are present over here, right? You would simply say that one phase is there, that is gas. Inside, gas is present. We don't know how many gases, but some sort of gas is present, right? So n number of gases are present, in that case, phase would be always 1. So in the yellow colored balloon, in the purple colored balloon, in both the cases, the number of phases would be 1. But the number of components would be different in both the cases. Okay. So in first case, in yellow color balloon, you can see that only oxygen is being filled. So only O2 is present. So number of components, 1. In yellow colored balloon, helium gas as well as oxygen gas, both are present. So the number of components would be 2. Okay. So if you have to simply calculate degree of freedom, now you know F is equal to C minus P plus 2. Remember that degree of freedom is also known as variance. So in this way, you can calculate degree of freedom, number of phases, and number of components. Now a question might arise. Why we are studying this? Okay, what is the reason of calculating the degree of freedom? You understood that we will require temperature, we will require pressure, we will require composition, all these independent variables. How many variables are required? All these things we can get it from the value of f. But what is the reason? What is the need of calculating this f? Okay, this question mark would be solved in next video. I hope you have understood how to calculate number of phases, components, and degree of freedom. Thank you.